mini and a main talk. This time we have a main talk because our speaker is awesome, so he counts for 2. There. I'm going to introduce him, and then whenever I introduce speakers, and I read their bio, and then we make something up about them, just to make something about them. Sean T. Allen. Do you like to be called Sean T? Yes.
Very complete.
Sean Allen is VP of Engineering. I think Sean T. Allen is VP of Engineering at Wallaroo Labs and a member of the Pony core team. His turn-ons include programming languages, distributed computing, Hiwatt amplifiers, and Fender Telecasters. His turn-offs, not that, I don't know why I know this about you now, include mayonnaise, stirring yogurt, and sloppy code. He's one of the authors of Storm Applied. Sean's favorite guilty pleasure is to recite 18th century poetry while wearing his favorite brightening face mask.
Woo!
Let's give it up for Sean.
Yeah. Skincare.
Oh, cool. There's the stuff. Yeah, hi. My name's Sean T. Allen. Seeing how you emphasize that, I feel like I'm going to have to tell the story. So years ago, I just went by my first name and last name, like most people usually do. And at some point along the line, whenever you'd Google my name, a couple things came up. One of them was a real estate agent in Arizona who sold a lot of stuff, and that wasn't particularly bad. There was also a guy who's a professional weightlifter, also not particularly bad. But for a while, the #1 result was a guy who'd been arrested for selling meth in a fairly violent incident in North Carolina. And I decided, I'm trying to have a professional career, and maybe I'll add something in there so that I'll show up instead of the North Carolina meth head. So now, yes, always going with the T. I think Inez gave a lot of information about me. Those are all Twitter things that get to me. The one thing that she didn't add there is that I also love French street art, so all the photos in this, almost all of them are French street art. I'm talking tonight about a paper that I love. I know it's called Papers We Love, but you know, I don't know if everybody always actually talks about papers that they love. This might be my favorite paper. It's either this one or Peter Alvaro, who's over there, wrote a paper called Molly, Lineage-Driven Fault Injection. It's head and head between the two of them. They can duke it out. If Pat Helland had actually come, we maybe could have had a little fight to determine which one is my favorite. But yeah, we didn't. I've given multiple talks that are about this paper where they all pretty much start the same way, with me rambling and then talking about the paper, and then they all go off in a whole lot of different directions. And I think this is because there's a quality to Pat Helland's papers that I really love. For lack of a better term, his papers are abstract. They give you they're more descriptive of a way that you could go about doing things rather than a lot of papers which are very prescriptive and say, hey, this is what we did, right? And Pat's is more like, this is sort of an approach that you could follow to get some type of great result that you might be looking for. And there's an awful lot of wiggle room within the space that his papers create. A friend of mine, who is also a colleague of mine, likes to describe them as engineering rather than computer science papers. That means something to me and folks who I know. Maybe that'll mean something to you. Maybe it'll just be a phrase where you're like, I have no idea what that means. But some folks might know what that means. So, yeah, that's kind of like why I love Pat's papers. And tonight I'm going to be talking about Life Beyond Distributed Transactions and Apostate's Opinion. A paper that I love so much, it is my favorite, that almost every single time I say the name of it, except for that one right there, I usually get the name of the paper wrong. But there we go. So there was an original version of this paper that came out in 2007, and then an updated and abridged version that came out in 2016. There's some differences that I wanted to talk about between them, but I realized I couldn't actually I couldn't actually figure out the words in order to describe the differences between them. It's sort of there's a feel that's different between them, and you feel like the audience is different. So if you haven't read both versions of it, or or if you have only read one, or you haven't read none, if you go out and check it out later on, I would suggest reading both the papers, because they are differently written to speak to some type of different audience. Both of the papers, however, in general, are what I like to call they're database-centric. Pat, came up with, he had Jim Gray, who's one of the greats in the database field, as his mentor. An awful lot of the stuff that Pat's done over the course of his career has been in the space of databases. But one of the things that I love about this paper, and as I said in general about a lot of his papers, is that there's a lot of wiggle room. And even though he really talks about a lot of things in the paper from the standpoint of somebody who's worked with databases all their lives, it's really more, this is a paper about applications that care about state, right? The fact is that most of us, when we think about an application that cares about state, we think about a database. But that doesn't have to be the only thing that's there. And so like the company that I'm at, it's called Wallaroo, Wallaroo Labs. We're building a distributed stream processor called Wallaroo. And we like to say that what we're building was inspired by this paper. That's kind of revisionist history and a lie. What actually happened was we started building this thing, and then like a year and a half into building it, a colleague of mine came and said, hey, I found a paper and it describes really well like a nice chunk of what we're doing, and I really latched onto the paper because of that, where it gave us as a team a vocabulary to talk about what we're doing. And I think that's a quality that a lot of Pat's papers have as well, where he's taking this general kind of thing that a lot of people could approach and talk about, and he's giving them a language to talk about the way that you can do that. So yeah, this paper in particular it's about how you can scale stateful applications, at least in theory, infinitely, right? And I'll get into what scale means in a little bit. But so in the rest of this talk, what I want to do for the general outline of this is I'm going to talk about some axioms that you're going to have to accept in order to get the two big ideas from Pat's paper that I'm going to talk about afterwards. You could cover those axioms, but those axioms really, and then I have links at the end. There's a number of papers where you could do a Papers We Love, where you talk about 3 or more papers from some folks like Peter Bayless, coordination avoidance in database systems and whatnot. So you're going to have to accept those axioms. I'm going to cover the 2 big ideas that are in the paper, and then I'm going to talk through like a real-world example of what an application that put these into practice is. And I'm going to do that by explaining an application that we actually wrote as one of the things when we were building Wallaroo, because in the end, this is the particular real-world implementation of these ideas that I know best. So, axioms, right? These are ones that in order to get anything out of the talk, well, you can still get something out of the talk, but even if you don't necessarily agree with all of these axioms, just suspension of disbelief for a little bit, don't break the fourth wall, and let's go ahead and let's just go with them. So the first one is that in order to scale infinitely, we have to scale horizontally. This is going to be one of our axioms. I'm not going to attempt to prove this. The basic idea is that there are 2 general ways that you can scale an application. You can either scale it vertically or you can scale it horizontally. Vertically being, I'm going to add more memory, more CPU, more disk, whatever it is, to an individual machine so that I can continue to expand my processing capacity. And horizontally being that, hey, I might do some vertical scaling, but eventually I'm going to start adding more machines to this as well. I'm going to build a distributed system. I'm going to deal with all the fun that comes from distributed systems, but I'm going to be able to scale in this horizontal fashion. The next axiom that you're going to have to accept is that in order to scale infinitely, we have to avoid coordination. I can't really see much from the lights, but Peter looked like he loved that, so that was great. I feel like I've already succeeded in this. The big idea here is that in order to be able to continue to scale our applications, we have to be able to have all of the little bits of our applications to be able to work independently from one another. They cannot coordinate in any type of fashion. And really the big idea here that you'll see in a lot of stuff is really this idea in a lot of distributed systems of if you want to be able to scale, if you want to get performance, et cetera, you need to be able to operate on local knowledge, which to me, when I first encountered this in papers and everything, I loved it because I grew up as a military brat, and the #1 idea that the military teaches their troops is that you have to be able to act in a local fashion without having to check in with anybody else in order to find out what you should be doing. So this is our second axiom here, that in order to scale infinitely, we have to avoid coordination, right? Our third axiom that you have to accept, and this is the life beyond part of the title, is that distributed transactions are a form of coordination, right? And when we talk about a distributed transaction, we're really talking about, think about this right now in a database sense, where you have a database, say a relational database, which everybody should hopefully be familiar with, and you have transactions that you can run at. So you might have a table that's customer and orders, and I want to update both the customers and orders tables at one time, so I'm going to have a transaction which will update both of these. And they'll either succeed together or they'll fail together. We call it, they're an atomic unit in that particular case, right? But what we're saying here is that no, we cannot do distributed transactions within our system if we want to scale infinitely, because this is a form of coordination. So the axiom that we can derive from this is that in order to scale infinitely, we can't use transactions, right? We can't. So I keep talking about scaling and saying in order to scale. So I really want to talk about what is scaling, at least in terms of how it's defined in the paper, right? And it's a little differently than some folks might go into it thinking it is, but it makes a lot of sense if you're coming at it from kind of a database angle. The idea is that we're going to scale things within our system, like customers, orders, shipments, taxpayers, bank accounts, whatever that might be. We're going to have more and more of these things that we're going to accumulate over the course of time, where they're not going to get significantly bigger. Our customer records are not going to be 1K today and 1 gig tomorrow. But we might have 1,000 customers today, and we might have 1 million of them tomorrow, right? This is what we're talking about. We're talking about scaling. Talking about having an awful lot of all of these things together. If you're worrying about scaling, where it's really the size of your things is getting bigger, then this is not a paper in whose playground you should be looking in order to solve your problems, right? Because what we are doing is we are scaling these things, and these things have a name in the paper, and they're called entities, right? And this is an abstraction that exists within the paper. They are these things which are, as the definition has for it, is they live on a single machine and they are individually manipulated. That is, each entity lives somewhere within our system, and each one of them can be individually manipulated without touching any of the others, right? So an entity really can be anything which is defined by your application or your problem. Like we said before, it could be a customer, it can be an order. If you look at this from a way that you might do this in a database that we're used to, you might say, oh, okay, each of my tables in my relational database is an entity. And that's a reasonable first shot that you might make at it. And the one thing you'd have to go along with it is that every entity has some sort of unique identifier or key that we can use to address it. And if you're coming again at it from a relational database standpoint, you might look at that and go, oh, this is kind of like the primary key for this thing. However, there's an additional bit on what an entity is in this case, which is that an entity is an atomic bound for what you'd consider a transaction, right? Everything that we would need in order to do an atomic update has to exist within this entity. So if we're talking about things where we're dealing with customers and their orders, and we want to be able to update a customer at the same time as we're updating their orders, then that combination, that set right there, has to be, that's what our entity has to cover. It has to cover both a customer and the customer's orders. And And because our entities are separate from one another, like they have to be disjoint from one another. There can't be any overlap like between them at all, right? And then what we're going to do is we have these boundaries around entities for where they're atomic, so we can access them, and we can serialize access to them so that updates happen one at a time on them. Like, if you can imagine for a moment, like this comes in, it's in like a FIFO fashion. Here we have, if we could imagine there's some sort of global ordering for these things, right? We got update 1 and update 2, which are for Alice, and then we got update 3 down here for Bob, etc. And so what we're going to end up doing is update 1 for Alice will happen, right? And there will be no other updates for Alice happening at that particular point in time. We've got this queue, and we're going to go ahead and we're going to do this update. Then we would have our second update, which would get done, et cetera. We would work our way through this queue of updates that are going to happen for Alice. And all of these things which happen for Alice, they can be happening at the same time that we're also doing updates for Bob, because they are completely disjoint from one another, and there's no overlap between the data for Alice and the data for Bob. If you stop and look at this and pull back for a moment, you know, this sounds an awful lot like a key value store, where you've basically denormalized your data. And that's a good way, if you're getting into it, to think about it. It's probably a much better way to think about it if you're trying to imagine what this would look like, rather than more of the relational database. This is my table, here's my primary key on it, right? So that's idea number one. That's the big idea number one from the paper, is that we have this abstraction called entities, and we access them like independently of one another in this serial fashion. The other big idea is that we have a two-layer architecture, right? And this two-layer architecture has the two parts of it that we have, as Pat defines it, is that we have a scale-agnostic layer and we have a scale-aware layer. So the scale-agnostic layer is where your application logic, which doesn't need to know anything about scale, would go ahead and live. And the scale-aware layer is where you put all of your stuff. When we're talking about we're a distributed system. So your scale-aware layer is where your ability to hook nodes up to one another so that they can form this distributed system lives. This is where your knowledge of how, if a message comes in for a customer with an identifier of 1, how do we route that to whatever particular node this is actually supposed to be processed on? If we have a failure, how do we replay messages? Are we going to do at most once? Are we going to do at least once? How is this actually handled? All of this occurs in the scale-aware layer and is hidden away from the folks where you're actually writing your primary application logic. And then all of this is connected together through some type of API that your folks who are writing, your scale-agnostic code can use in order to access the scale-aware portion of everything that's there, right? So from this, I'm going to add one more axiom, but at least, we're building on the other axioms there, right? Which is that in order to scale this stuff infinitely, our business logic has to be independent of scale. The business logic, the application logic, whatever it is, we can't scale infinitely if we're going to have to sit there and start making changes to our business logic because we added an additional node or anything else. They have to be entirely separated away from one another. So, all right, those are really the two big ideas that are from the paper. And as I said in the beginning, what I love about Pat's papers is that really it is a description of like a type of system that you would build. There's some other ideas that are in the paper as well, but they're all just like, they're descriptive of this is how you could go about building an architecture like this, as compared to, a lot of papers where, it's very prescriptive and it has an awful lot of constraints on it and whatnot in order to make this thing actually work. And there are very few constraints on the ideas that are here. Really, the one big constraint that you have on the ideas in the paper is that you have to be able to take your data and break it up into these disjoint sets of things which are entities. As long as you can do that, then everything else in the paper should be able to flow from it, right? You could build a wide variety of systems using the ideas from this paper. Systems that if you looked at it just from the outside, people would go, those are completely different things. I can't see what they have in common with each other at all. But they could still be rooted right here, like the ideas of this. Like, just entirely separate systems. So, you know, the company I work at, we have built like a system that's like this, and I want to try and like give like some concrete examples of what an application built using this might look like. So a little bit about this. I work at a company called Wallaroo Labs, and we built a distributed stream processor. If you don't know what a stream processor is, but you know what Apache Storm is, or Flink or something, or maybe Google Dataflow, that would hopefully be in the right area. The basic idea is you have data that comes into a system in some theoretically non-ending fashion. You run some computations on it, and some results come out the backside, right? And in our particular case, we're building one, and this is where Pat's thing comes into it, where it's specifically designed to be stateful. It's designed for applications that need to accumulate some type of knowledge about what has come before so that they can make decisions about what comes later on. And I'll show that in an example that we have in a bit. And like I said in the beginning, this is a paper that's, while it's written from a database-centric standpoint, right, it doesn't have to be applied to databases. If you squint really hard, what we built, you could say, oh, there's some weird sort of database key value thing in there, but we never actually sat down and said, oh, we're going to write a database, right? But still, what we started doing, we found when we came in later on, hey, here's a paper which fits really well with what we've been doing. So, like entities from Pat's paper, we already had them, but we called them state objects, right? But it was the exact same thing. It had the exact same rules to it, which was really cool. So it gave us a nice way to talk about it. And we already had the two-layer architecture, except we called it scale independence instead of scale agnostic. You know, and you know, if I was to diagram this out, it ends up looking the same, except, you know, we specifically say, hey, our thing is a framework, so here's some logic that you plug in at certain points in order to get this stuff, you know, to run at certain places using our API that we give you, which is then going to run on our runtime, right? Woo! All right, and it is those are the two big ideas from the paper that are right there in it. So what I want to do is I want to actually show an application that implements this, a little bit of code from it. I'm not going to do all of the code from it. If anybody really wanted to afterwards, I could show you all the code. I could run demo stuff. So the example application I'm going to do is an application called Market Spread. And this is an application that you might want to run inside of a bank or some sort of trading organization. I know that you might want to because we built this as a prototype for a large bank. And the idea behind this application is that you have a trading organization where you're making algorithmic trades, and you want to be able to at some point go, there's something funky going on in the stock market with a particular stock, and we would like to start pulling back all of our open trades that are there for this stock. Honestly, I had not really worked in finance before I started at Wallaroo Labs, and I was like, I don't really understand why you could possibly need an application like this. And then, like, at some point after I started, there was this big news story about how like all trading had been shut down in Amazon because someone somewhere, and Cindy, you'll like this, someone rolled out a configuration change at the stock exchange, and suddenly Amazon was either trading for like 10 times more than what it had been actually at the close of business, or 10 times less, something like that, where if you got an algorithmic stuff going off of that, everything's going to go haywire, and you'd like to have some type of system in place in order to stop that. If you don't have a system in place in order to stop that, you could look up, what are they called, Knight Ridder or whatever it is. They don't exist anymore because they had an algorithmic trading system that had no checks on it like that. And it went a little out of control and put them out of business in about 45 minutes, where it lost billions of dollars, right? So that's the idea behind this application. And in order to have an application like this, if I was to describe it at a high level to you, right? This is kind of what it would look like, right? Just a diagram. We're going to have a couple sources of data. We're going to have market data. That's basically the term for, this is the continually changing like price related to a particular, particular stocks. Like this could be coming in for like Apple. I looked over there to see, another company that somebody worked at, and of course I looked at somebody who's from Apple. So IBM, there's another company. Or Microsoft, it's right down there. So, and then we're going to have a second stream of data, which is orders, and these are the orders that customers have placed, and we want to decide whether we want to issue a rejection for these or not, right? And we're going to need to check against it in some type of fashion. So, we have these rejections that will be coming out at the backside. This was a thing in this system. It would do absolutely nothing if things were working normally, right? It was running alongside a normal trading system, let everything happen, and its job was just to pull back orders if they needed to be. And so what you have is you have this data pipeline, right, of orders coming in, and it's got something like, hey, this is a trade, it's for Microsoft, and we need to check this trade for Microsoft against, let's just call it an amorphous blob right now, of state, and if there's something funky going on with Microsoft, we're going to go ahead and issue a rejection. And we have a second data stream, right, which is, it's market data, and what we're basically doing with this is we're updating, like, the state, like, what's going on with Apple, et cetera, and we're going to do those types of updates, right? So I'm going to show you what the application definition for this looks like in a scale agnostic fashion inside of Wallaroo, right? This is the Python code because we have a Python API. This is the Python code in order to set up that same application here. And you'll see what we have here is we have a couple data pipelines. This is the order pipeline here, right? And this is our market data pipeline right here, defining both of these. And we're defining the sources of where our particular data happens to be coming from. This is an important part of getting one of those together. And we also define the operations that might be happening on this data, right? And you can see here, for example, this is, we're going to see this in a little bit. We're going to run this thing called check order on all of the orders that's going to happen against this particular bit of state that's here, right? And we have another one down here for update market data. And lastly, we have some sinks where any output would go. So if you look, for example, at the order one, there's some output that would be going out over TCP. And for the market data one, like we said, there's no actual output from that. It's just updating state. I'm showing you all of this Python code because in the end, this API is scale independent. It's scale agnostic. There's nothing in here about the number of machines that this is running on, et cetera. I can take this application and I can run it on using one Python process. I can run it using 5. I can run it using 10 without having to make any changes to the code, right? So something like this is what you could imagine like your API for some scale agnostic code along the lines of what Pat is talking about looking like, except ours happens to be for streaming data pipelines. So it could look entirely different if you were doing this for something that's not like a stream processor, but the same basic qualities would be there of you're only talking about the logic, sources of data, where the data is going, and the operations that you're doing on it. So before, when I had that little graph for the stuff that was up there, I talked about, user-supplied logic was one of those. And, this is an example. This is the update market data code from this. It's slightly simplified, but it's doing some basic finance stuff on it. I used to remember why this was important and what it did because I got a crash course in all of this stuff when we were working with the bank. But honestly, I don't really remember like what the logic that's in there now. And there's a lot of Wallaroo specific stuff in it. But the big thing you would see here is that if you're a Python person, or even if you're not, you can trust me on this. There's nothing in here, again, that's about scale. We're keeping all of our logic independent of the scale that it's running at, right? And all of this then happens inside of a runtime, which is actually responsible for all of this stuff. In the case of Wallaroo, right, what we have is we have a Python interpreter, which is embedded inside an awful lot of native code that we wrote in a language that nobody's ever heard of called Pony, which has worked out very well for us for the most part. But sorry, I'm on the Pony core team now, so I always like to get the little Pony thing in there. You should go look, ponylang.org, for everybody who's watching on the live stream. But okay, so this runtime here, right? We have this logic which is going to run on top of it, which is completely independent. So the Wallaroo runtime, you're able to hook up different, basically different Python interpreters to one another, and we're going to take that logic and we're going to spread like everything out like all over the place, and it's going to handle like the message routing, etc. Like we do. Let's see. Let's call it exactly once. We like message delivery between things, but unlike people who get in trouble on the internet, hi Confluent person, I'm going to actually define what that means. So inside there we do at least once message delivery. I was really hoping you would come so I can make that joke. We do at least once message delivery, where then we do deduplication if we have to send a message a second time. And that's what I mean by exactly once. If there's anybody here from Streamlio, that's effectively exactly once. Hey, effectively exactly once, which is actually probably a better term, but nobody's ever heard it. All right, so this is in there, all of this good, fun runtime stuff, and if you really want to know more about all the stuff that's in the runtime, we can talk about it. But the thing that I really want to talk about is state objects, because in the end, this is a paper that's about state and how do we do state and how do we do all of this. So before I said, hey, you could think of it kind of like a big key value store. And if you're thinking of it as like a big key value store, then, well, maybe we could think of it as one big map, right? It's kind of like a thing. There's a bunch of things in there that got identifiers for them. And yeah, you know, we could kind of think of that. With the market data, when we're updating stuff, hey, there's this stream of stuff that comes in and it's updating this big amorphous blob of state. Or, you know, more closely, it's like, okay, well, there's identifiers for each of these things. So there's going to be the little individual ones. You know, it's a map. We got a key for like Microsoft, you know, so that we can go ahead and we can update our Microsoft entry, et cetera. And this is at least conceptually a good way to really start thinking about how you would actually implement this stuff. Except that, you know, rather than just being one big map, it's a big map that you have to distribute across the whole lot of machines, right? So you're going to have to do some kind of partitioning across, you know, across all of this. And there's a lot of wonderful papers out there about various ways that you can do hash partitioning. A lot of people do stuff based on the original Dynamo paper that Amazon put out. There's links to, in the stuff that I have at the end of this, to a paper on random slicing, which is what we do, and also a really excellent Medium post. Never thought I'd say that. A really excellent Medium post on a critique of how like the hash partitioning is done inside of Dynamo, as described in the DynamoDB paper. But this is something you would have to do, is you're going to divide this up in some fashion. So while you can think of it as a big giant map, think of it as a big giant map that happens to live all over the place. And when you go to do an operation on it, if you're on machine A, the operation might actually happen on machine B, right? So in the case of our market spread example, we have a bunch of these little entities, these little state objects, and they all exist on our single worker that we have right now, just one Python process, right? They're all living there together. They're very happy. They're living in peace and harmony. And now we're going to go ahead and we're going to add another worker, right? And this worker initially starts with no entities on it, which, given the fact that we're scaling entities, this is a pretty useless state for our system to be in, because we've added another worker, it's taking up resources, and it's doing us absolutely no good because it's just empty, right? So at least on a naive level, this is how you can think about what would happen inside of a system like this. In order to actually implement like hash partitioning things effectively, you wouldn't actually end up with something as naive as what I'm going to describe, but it's a good way to think about how you would actually be doing this if you're building a system. So we have these two workers now. What we can do is we can take the state for IBM, for example, right? And we're going to serialize the state. I'm going to send it across the wire so that it goes from worker 1 to worker 2, where we're going to go ahead and deserialize it. Now IBM exists over here. In any future things where we want to do something which is addressed to IBM, we'll go ahead and it'll happen on this worker instead. Our messages will be rerouted there. We can do the same thing, right, where we're going to take Microsoft, go ahead, we serialize it, send it across the wire, and boom, there we go. It ends up on our second worker. And at least in our naive case, right, we have this nice, wonderfully balanced thing where we have an equal number of entities on each one of those. You wouldn't actually want to do the naive thing here in a real-world scenario. And the clue to that is that in order to get this naive setting, you need an awful lot of coordination between nodes in order to make this happen. And it's problematic. So you'd want to have something which can operate on local knowledge. The random slicing paper is a really good example of that in the links later. But effectively, this is really, if you're thinking about this, this is what you'd want to do, right? Then state objects, right? This is something, there's absolutely nothing in Pat's paper about what does an entity look like, what are the properties of an entity, really beyond the fact that, hey, it's disjoint and you operate on them one at a time. So when we sat down to build this, our first initial idea, because, you know, we love computer science papers or something, who knows, was, ooh, let's put some CRDTs in there, right? Let's put some CRDTs in there. We didn't end up putting CRDTs in there, because what we realized, at least in our particular case, was we were really trying to target people who would know nothing about CRDTs. And in order to implement CRDTs, you would have to ask people, hey, here's these few basic CRDT primitives that exist. Go build your application using these, which we thought was really way too much of a jump for people to make. So this is what our state objects, right, our entities look like. They're really boring, but you'd probably end up with something like this if you're doing it as well. It's just, for whatever your language is, it's just a regular old, you know, boring data class type thing. You know, if you're doing closure, I suppose it could be, you know, like a tuple with a map or whatever these types of things are. So, yeah, I mean, that's a basic example of like what you can imagine, you know, like this stuff from Pat's paper might look like. Hopefully, you know, hopefully between like the actual description of what Pat writes about and a real world example of what you might go about building that looks like that. Some of you would be like, get interested in this, want to check it out more, etc. Yeah, and there's an awful lot of stuff here in this GitHub repo, which is links to various different things, including, I'm going to keep making this comment, including Pat's Twitter. Pat does not tweet very much, but it seems like every single time after I publicly say Pat doesn't tweet very much, he starts tweeting for a little bit. So that's really kind of fun. There's, like I said, this is the third time I've done this talk now, and the content's been different for each time. There's slides to different ones there. There's a link for when I did this at VelocityConf in San Jose, like a month ago, where instead of giving an example at the end, I actually talked about all of the things you would have to worry about if you wanted to go out and build a real-world example of this. So as long as you can put up with how many times I say during that video, and also you won't be offended by my ragging on Pearl Jam at the beginning, then it's probably something you should check out. There's an awful lot of stuff in the links there. There's a couple links to papers by Peter Bayless, which would help support the coordination axioms that are there at the beginning. There's some links to things like BOS, because why not, right? There's actually a reason for that, but it's there. So yeah, that's it, and thank you.
All right.
Questions?
I have one at the beginning. Do you not have a photo of yourself and Pat Helland?
I do have a photo of me and Pat Helland.
Ooh.
Wait, does anybody need this right now? Hold on. Wait. I'll put it back up in a moment.
Okay, good.
It's easier for me to go to, oh no. Oh, no, wait, no, I can do this. I am a computer science professional. I'm sure I can make presentation software bend to my will by first mirroring my screen. Oh no, apparently I can't. Oh yes, there we go.
Courtney, just pass your phone around, right?
Okay, and now we've lost it up there. So if you still need the URL, it's here on the thing. If you go to my Twitter, which was there at the beginning, is also in the links. The thing which is on there as the pinned tweet for mine is a picture of Pat Helland, who came to my talk at Velocity Conference, surprised me. He was hiding in the back with a baseball cap on so that he wouldn't freak me out. Oh, I'm sorry. I'm a bad person with the microphone. Yeah, so he wouldn't freak me out. And there's a picture at the end of him and I standing underneath the big thing that says Pat Helland and me. So that was kind of cool. But.
Yeah, got it. You do you.
Okay.
I have a question. Hello.
Hi, Peter.
Hello. You made a few mentions of random hash partitioning.
The random slicing.
Random slicing.
Yeah.
Thanks. Can you say like a few more words about that, especially as it contrasts to like Vino-based partitioning in Dynamo?
I could. I am far from an expert on it. I work with Scott Fritchie, who some people might know. He used to work at Basho. He's an incredibly smart person, and he knows far more about the Dynamo stuff and everything else. Honestly, I would do a really bad job on this. I'll say this. InfoQ should be publishing an article sometime next month, which goes into that topic in great detail. And Scott would do a better job than I ever would in terms of the types of problems that exist within Dynamo systems, in particular like REAC, that the random slicing algorithm can solve.
Hi, Sean.
Hi, Peter.
So,
Wait, whoa, stacking up the Peters. Okay.
So, yeah, so I totally agree, right? That coordination is the most evil of the evils to be avoided for systems that we want to have go fast. But usually the story that I tell and I hear told, it takes a while to back into why we're coordinating at all, right? So the story might be something like, oh, so you have these systems that run on lots of computers, but some of the computers could fail. And so you need to have multiple computers do the same thing, like via replication or via upstream backup maybe. Like I'm not sure what your fault tolerance strategies are in the streaming system, but you make multiple copies of things so that you can lose some of them. Oh no, and now you have to be worried about the multiple copies of things like being the same, agreeing with each other. And that's when you typically pay that cost of coordination. Now we're going to do Paxos to make sure that the different replicas of these streaming operators have the same state at every time or something like that. So my question is, what is the fault tolerance story for Wallaroo?
So that sounds like such a question that would come from somebody who's coming from a database-centric standpoint. And I don't mean that in a bad way. Because like when we're talking about it inside of a streaming system, coordination needs a lot more to us. Like even not just in streaming, but inside of a thing that's like PATs, right? Like how do you do message routing, right? The simplest way that you can do message routing is you can have a thing that exists inside of every single process that you have that knows how to route, period, to everything. And it becomes a source of coordination, a bottleneck, because everything has to send messages to it when routing is going to change, and everything has to go through it in order to be routed. This was actually, we put this in the first version of our thing that we built. It was great. It was awesome. We were really happy to set it up and watch it start running. It was slightly slower than our 100% pure Python, no native code or anything else version. It was so slow, it was kind of depressing. And when we went back and removed that sort of coordination from it, instead of processing 18,000 messages a second for our test application, we were processing 3 million. Right? So there is that, at least that. In terms of the fault tolerance in Wallaroo, we do two things. After reading a whole bunch of academic papers, all of which had constraints for how you do fault tolerance in a streaming system, none of which actually felt like realistic. Was that what we do is there's a transaction log, like I said, it looks sort of like a database thing, where we write out everything that has happened in terms of updates to state objects on a given node. If that node fails, well, the worker fails, and it's restarted, we can reread from that locally. And then we also have this server, which we really need to rename. So we call it S0, right? Because it's an awful lot like S3, except we stripped away all of the stuff that we don't need. We need to rename it because in conversations we keep calling it S3 instead of S0, which leads to no end of confusion. And so we also write that same stuff out to an S0 server. I almost called it S3. We write it out to an S0 server, and you can have multiple ones of those. And then if you lose like an entire machine, for example, when you bring them back up, you can go ahead and there's a recovery protocol where you read from that.
You synchronously write these logs to the
Yes, we asynchronously write the logs, yes. Our first version before the S0 stuff actually isn't released. It's not coming out till September. Our first version was to tell people, hey, you can write this to like some type of durable network type storage. Everybody thinks that's an awful idea, which is why I loved it so much when I was at Velocity, and people explained to me how stateful applications work inside of Kubernetes. Because I was like, oh, that sounds remarkably familiar. I'm going to guess that we could probably sell like the Kubernetes solution to everybody who was like, no, your solution is really bad. So, but yes.
Thank you, Sean.
Oh, we got two people with mics. We're going to have a race here.
Oh, I also love Pat Helland, thanks to you now.
Awesome. That is great. More people should love Pat. Pat is also, he is one of the nicest people that I've met.
Yeah, I'm totally getting a picture with him, like you did.
I came up as a musician, right? So I met an awful lot of people who you might classify as heroes, you know, at some point. And, you know, it's really nice when you meet one who's really nice like Pat Helland as compared to, you know, like when I met Lou Reed, for example, right? Entirely different scenario there. Oh, I still love Lou Reed's music, but oh man, that guy's an asshole. Well, he's dead now, so.
God bless his soul, I guess. I don't know. But the question is, so you described how these entities are now the points of coordination, right? So doesn't that move the horizontal scaling to like these entity objects in some sense? Like now they're like the point of coordination, right? In a way.
In the sense that you can only update, you can only have one update going to the entity at a particular point in time? Yes. Now, if you wanted to be able to make multiple updates to an entity at one time, you could add a twist to Pat's idea. You can make all of your entities be this really fancy academic data structure called a CRDT, right? Which would then allow you to be able to make writes to multiple different copies of it where they could eventually converge on the same value, but you'd have to be willing to accept some eventual consistency. So there's still wiggle room within the idea of what's there. But yeah, I mean, effectively, you are serializing on this. How many people in here know Erlang or Elixir or Akka or any of those? Okay, how many of you said, wow, that sounds like an actor? Okay, so the language that we wrote all of this in is Pony. It's an actor-based language. Every single one of our state objects has an actor which actually manages it. Yeah, so.
So this paper came out in 2007 when everyone was going to NoSQL stores. And then we have now Spanner, where Google has sort of said that we don't want to avoid coordination. We want to have like distributed transactions at scale, and we can do that. And then there is Amazon Aurora, and they're the fastest growing service in AWS. So there are a lot of people who need distributed transactions. And
I would disagree with that statement. There are a lot of people, they don't necessarily need distributed transactions. They want an abstraction that gives them the same affordances that they got from transactions. I think that's an important difference, right? In that whatever the quality is in terms of your programming model that you're looking for with a distributed transaction, right? You can potentially get that from something else, and what you actually want for it. So there's some really interesting stuff that Chris Micklejohn has done with LASP, where there's a lot of times where you don't actually need the full level of coordination that you might get from distributed transactions. Sometimes you do, sometimes you don't, right? So I'm not really disagreeing with you. I would just want to rephrase it and say that people want the affordances that they can get from that. There's a style of programming that's easier there, but this is also a style of programming that when you're talking about distributed transactions, you're sort of ignoring like physics and the fact that two things can't actually perceive this. will not actually perceive the same value of something because light is getting there at a different point in time. And you're going to put some locks, et cetera, around things. You're going to have a programming model where you're saying, I really like this and this is good, but at the same time you can also introduce things where when you start having locks and transactions and everything else, you get an entirely different set of things that happen, right? So
well, locks is a way of giving transactions. There can be different other ways of giving.
I agree.
But my question was, how widely applicable you think it's in the current day when there are a lot of enterprise databases and everyone has a distributed database, how widely acceptable it is now to not have complete no coordination versus maybe going out the way of Spanner where you have the opportunity to have that and you can avoid it in some cases.
Because you can use something, it doesn't mean that the problem goes away, right?
I would say this. No solution is right for every single problem, right? There are some things where you would very much want those affordances. There are other times when you don't need them, right, et cetera. And it's really a case by case basis of what you may or may not need, right? Like, there's a reason why lots of people use Redis for some stuff and Memcache for others, and everybody's not just using a relational database for everything they do. You need a different set of guarantees for whatever you might be doing for a different problem.
Hey, I'm going to race for the mic, sorry. Hi, great talk, thank you. My name's Henry.
Oh, are you Henry R?
Yes, I'm the guy who argues with them about exactly once. So, thank you. So I'm going to follow on a little bit from his question and attack a different aspect of this. I think this paper is wonderful. But if you look at the last 10 years, I actually agree with, I think, the perspective you were trying to get to, which is academia and industry has like moved away from the idea that a complete lack of coordination is where you want to go. But this paper did capture like the 2007 NoSQL zeitgeist very accurately. The axioms you said at the beginning have another interesting aspect, which is if you're going to scale infinitely, you need X, you need Y, you need Z.
Yep.
I work at a big data company.
I know.
No one needs to scale infinitely. How much of this do you think is still applicable when you say, if you just want to scale a little bit?
I mean, I think that really depends. Like, I can't answer that because, so, let's see. Other than getting on stage and saying things that I didn't intend to say, where I try to be really good in public all the time. Other than that, my brand, probably more than anything else, is to be ambivalent about pretty much everything in the entire world. And the answer for everything that I usually give is, it depends, right? And I mean, I'm never comfortable sitting down and going, oh, well, for that particular generic case, you know, you should use X, Y, Z, because I think there's a lot more things that certainly go into it, right? For an awful lot of people, like the guarantees that you would get from a relational database, for example, are something that they would probably really want and they would not want to give up, right? That is a thing that they wouldn't want to give up. On the other hand, right? Like, you can take the ideas from this, and these actually describe reasonably well how if you wanted to take like a lot of the systems that like banks use for high-speed trading or whatever, they start, if you squint, they look kind of like this, and so I mean, it really depends on your particular thing and what you're doing with that data. You might you potentially wouldn't ever do this as your system of record because you do have these disjoint sets, and you're going to end up in this horrible situation where you can't do ad hoc querying easily against the data that you have, et cetera. That could be incredibly important to you. You might still have a system of record somewhere. You could, I don't know, you could write all of the things that come in, and you could write it to, I don't know, some type of durable log, which is distributed across a bunch of disks or whatever, right? And hook up some stuff to take that and put it into a database, a relational database where you're going to do all of that. And you could also have some systems which look more like this, where you're answering like these types of problems where you want to be able to scale them. I mean, it really depends on like the problem set there for the person. Yeah. No hammer is ever right for driving in all of the screws.
So thank you for the talk, super interesting. So this is super weird for me because I work on Cloud Data Store and I work on upgrading it. I'm working on the live upgrade to Firestore. So my day-to-day is literally Megastore and Spanner. And I didn't realize it before tonight, but I literally just went and looked at the Megastore paper, and it cites Pat Helland's paper, the one you just talked about. So the question for you is, how do you convince customers that this is potentially the right model for them? Because for us, the biggest reason we're doing this for our customers is because so many people have come to us and said, like, we want in Pat Helland terminology, cross-entity transactions, and we don't want a limit on them. How do you give this to us?
Well, that's fine. They have a constraint which is really important to them, right? And they will give up things because of that, and that's a perfectly reasonable thing to do. Like, I don't have the problem of selling people on that, because the people who come to me are folks who are trying to solve a different problem, right? They're trying to solve this different problem where, in the end, I'm not building a system of record either, right? I'm building a system which is designed to, I want to be able to take this and I want to scale up and down the number of nodes which are doing this stream processing, where for a specific application I can make quick decisions based on some data that's there, rather than having it stuck in a database and constantly being making round-trip trips to a database. So I don't ever have to sell them on that. I'm selling them on other features there, right?
Sure, but what about future-proofing? No one knows all the features they're going to need in the future. And so have you had customers come back and say well, we thought we were okay with these limitations, and now we realize we're not okay?
No, but we're a very young startup,
okay.
So
okay.
But I mean, you can have that. You can have that happen for everything. I mean, there's a set of things that you're accepting there, an awful lot of trade-offs that come from it. I don't think I love this paper. I love the ideas in the paper. I can't imagine myself ever telling somebody that their system of record should be a storage system which stores all of your data as these disjoint sets, because the whole reason why it's your system of record is it's a place to go to answer questions that you don't know what they are yet, right? This is for systems where you already know what the questions that you want answered are, and you want to be able to scale the ability to answer those questions to a really large level where you're feeling comfortable that you could keep going and going with it, right? That's what it's for. It's not for answering unknown questions in the future. There are you got relational databases for it. I know that Confluent loves to sell Kafka as a thing that will allow you to do that as well. I mean, there are better ways to go about answering those. No?
So your comment was that this is not for systems of records or answering unknown questions, but the whole denormalize everything was made popular by Google doing this for Google search, which arguably didn't know what all the questions were yet.
Okay, so that's an interesting idea from the definition of question there. I meant question there as in order to be able to efficiently, when you have any type of database thing, in order to be able to efficiently be able to do ad hoc things against it, right? There are ways that you can do this so that you can structure it so it's good for answering a couple things, right? Like a key value thing where it's there's a bit about secondary indices in Pat's paper. I didn't touch on it, but I mean, if you've used the key value store, then secondary indices have probably been really painful for you, et cetera, because they're not designed to do that. Whereas a relational database, whether it's distributed or not, it could be Spanner, et cetera, everything else, is designed to be able to do that. But if I know specifically what it is that I want to go look up, and I have to do a join across 3 or 4 tables, then in all likelihood, an equally engineered relational thing is going to perform worse than the thing where I just have to go look up a single key in order to pull this data back, right? And that's really what I mean by the questions, knowing the questions ahead of time, where it's okay, I need to get some information from the entity with the ID of 42, and everything will be in there, rather than having to go collect this across multiple tables. And there are advantages and disadvantages to that.
Okay, so since I have the mic, I'm going to ask a question that is a combination of these two questions. Okay, so then we started with this thing that if we want to scale infinitely, like this is one model to approach us. Mm-hmm. That was like okay in 2000, whatever, 7, and then just like that was the ethos of the time. And then maybe we just realized that maybe coordination is so wrong, and maybe Henry comes and says like maybe nobody fucking has to like scale infinitely, and maybe we just want to like at least put a range or put a cap on how much we want to scale. Do you think that maybe things that are like infinitely versus not infinitely comes from like a matter of perspective? It's like whenever you come as a company, they're like, we want to scale to infinity and beyond because we're very optimistic. Whereas in terms of like what we actually have to build has to be like what's good enough for the next milestone. What are your feels on that? It's like, because like, we're building things that carry that assumption of how far we're going to go. Since you have like you're selling us the point of like infinity and beyond, or not selling, like just like you're like arguing that side.
Not the beyond. That's only in the title.
Okay, so then how do you think about it? Is it because like we're overly optimistic, or we just don't want to think about in terms of constraints and how we would design the system for the next stage of growth?
So I think at least one of the important parts in the scaling infinitely thing in Pat's paper is that you're scaling one specific thing infinitely. You're scaling entities, things that you would have reason to expect that as your company grows or does well, you would have more and more and more of these things. It's in like I've previously in the past, when Pat was in the audience, I've conflated scaling, like the way that people often think about it in terms of like being able to handle more throughput or whatever, with the scaling of entities. And he very politely each time after I do that in a talk is like, you did that conflating thing again then. Because when we think about scaling, like most of us usually think about scaling in terms of the how many requests can my website take, or how many what's the benchmark with the transactions per second, TPS. Yes. Yeah. Isn't that also the movie that I don't like? Is there? Are those also the reports that the guy has to put in? Yeah. Okay, that's what I got thrown by. Okay. TPC. Oh, thank you. Thank you. It was the same. Yeah. Okay. But so we often think about like scaling in that type of sense, right? That we're scaling for that, and that's not really what the paper is about. It's about scaling those entities, things that we could have a reasonable expectation that these should keep growing. We should have, as a business, we should have more customers. We should have more orders, et cetera. So I think it's a little different there. And when I first I mean, I still do it. I've read the paper tons of times. I built a system that uses like a lot of the ideas from it, but I still conflate like the one type of scaling with another because, I'm trying to sell stuff to people, and that's at least an equally large part of what, they're trying to do. And, particularly we started out like trying to sell to banks. We moved away from trying to sell to banks, but a huge thing there for them was how much can we process in an individual point in time? And like that was at least a decent part of a different scaling story with them. So, I mean, I've met plenty of people. Like I used to, I wrote a book on Apache Storm. It's a different stream processing thing. And after the book came out, people used to be like, hey, can you do a little bit of consulting for us and tell us if our problem fits like with this thing? And then they'd be like, sure, and go in and talk to them and be like, we're really worried that Storm won't be able to handle like our workload. It's really, really, really intense. And I'd be like, okay, so what are you talking about here? And they'd be like, we're doing a couple thousand messages. And I'd be like, you like couple thousand what? And they're like, a minute. Right? Like there's some people who are laughing, but I mean like there's a legitimate thing there. I'm not like it's like those ideas of what you need in order to scale are like in terms of that level are definitely dependent upon like the experience that everybody has and everything. As much as I hate it, because I am at heart I am an ass like most people. I go and I see blog posts that make it onto Hacker News sometime or whatever, and I go look at like the rate that people were talking about, like, oh my God, we did this amazing thing, and I just look at it and go, I'm like, what are you talking about? That's so easy, right? It's like in my head, I'm that person who's like, oh, you don't have big data. You could do that on one machine with SED, right? Like, I mean, but there are people who just, they don't actually have that, like, that understanding and grounding on it. So I'd say, yeah, sure. I don't know how I ended up here. This is why I love you, because this is how our conversations usually go, where one of us eventually goes, wait, what?
Yeah.
So what?
Any other questions? And we're gonna end up in another. No. If there's no questions, oh, over there. Go.
Hi.
Hi.
Good talk.
Thank you.
I hope that this is on topic enough, but I want to know, Pony is like super cool, right? So I have to ask, what about this, your project made you choose Pony? Like I know systems like this sort of work well in actor, in the actor model, but why Pony specifically? Could you just talk a little bit about that?
This is being live streamed, right?
But I don't think we can cut
and
it.
recorded. No, it's fine. It's recorded. So I'm going to give the nice version.
Nobody's watching.
Well, no, because I am now a member of the Pony core team, right? And there's this horrible thing that we do as engineers, which is where we insult other people's projects, either intentionally or not intentionally. And I'm sure that when I've answered this sometimes for folks, I probably said things that were accidentally insulting against things that I didn't mean to be. Somebody got really angry at me once because, for example, when we were first building this, our target customers were big banks where we were going to be doing like risk-type analysis things, where the big goal for this was to be able to respond to stuff that's measured in like microseconds, where we wanted like median latencies of like 1 microsecond, and if like the 99.99 was above a millisecond, they were going to be like, your thing is crap, even if that was so much better than like the existing systems that they had. And so we were looking for something that was going to be able to go really fast, right, and was going to was also going to have, these great latency characteristics, et cetera, and everything. It was going to be good for a distributed system. So there were a few things we went into this. Like one of the first things we thought of was Erlang. And I have a lot of friends who worked at Basho, and we talked to them about these are the things we want to do. And we eliminated Erlang from our list, for example, because the folks who I really trust who worked at Basho were like, we don't think you're going to be able to get what you want to out of it. And we ended up looking at a number of languages, just to talk about a couple of them, C and C++. In the end, I am a C programmer at heart. I realized this, like everything I think of when I think of computer problems always involves pointers to something that's over there anywhere. I've probably committed more like, pointer magic sins than anybody should have a quota for during the course of their life. But one of the things I did is like I started off writing lots of high performance like network systems years and years ago in C, and I learned C because C gave me this warm, happy feeling where it was really easy to get it to compile, right? At the time I was learning both C and Ada, and oh my God, Ada killed me. Oh, like I couldn't get it to compile. I felt like I was learning, and I felt awful. Like if you want to have imposter syndrome, or you want to give somebody imposter syndrome when they're a young programmer, put them down in front of an Ada compiler. They're going to feel completely useless. So I learned C, and it was great. C made me feel really good, and then I segfaulted and segfaulted and segfaulted and segfaulted, and spent years segfaulting and introducing weird race conditions and everything else. And so C and C++ had those characteristics, but I was really worried about, based on the people we could hire, and even just myself knowing it, that like, can we actually write a system where we want to have these guarantees about the data and not screw this up? And the honest answer to yourself after thinking, sure, I can do that, is no, I can't. I'm not going to be able to, and I shouldn't actually also trust any of my coworkers to. And one of the things that I liked about Pony was I came up with this whole elaborate set of rules when I was writing C, like threaded C code, for what is safe to do and what is not safe to do with data. And as long as I followed those rules, everything would be fine. The problem is I'm a human, and I would end up forgetting like what those rules are. And one of the big aha moments I had with Pony was I was sitting there, and the Pony compiler was making me feel bad, and it wasn't compiling my code. And I'm like, why are you complaining? And it was, oh, hey, look. Eventually I realized, oh my God, that's an unsafe thing to be doing with memory here. I'm introducing a data race here, and It's like, okay, I spent 20 minutes figuring out what the compiler was trying to tell me. If I'd actually been doing this with a language that didn't have that compiler, I would have probably spent years trying to locate where this weird-ass condition for stuff going wrong was. So that was at least a big part of it. But you can get that in something like Rust, right?
Yeah, so why not Rust?
The reason why we didn't go with Rust more than anything else was that we had an idea of what we wanted the runtime for us to provide, and a big part of that was to have where we wanted to have, because this is the right, if you want to write fast software, then what you want is you want to do asynchronous stuff more than anything else. These are my beliefs. I'm sorry if you disagree with them. And that you want to have a single thread per CPU core, right? This can make things nice and cache friendly. You want to make sure that as much as possible you keep the data that you're operating on a single CPU, et cetera. And there's nothing like that for Rust, right? And we would have to write a runtime that would, in order to do that for us. And if we went with Pony, which was a more immature language, et cetera, and whatnot, we would have that runtime that was already there. Just hand-waving, I think that using that runtime and contributing stuff to it probably got us 12 to 18 months, where otherwise we would have been writing the runtime and getting it really solid and locked down. It didn't hurt that Pony kind of ticks off all the little boxes for me for what I'd look for in a language beyond that, which is not surprising. Sylvan Klebsch, who created the language, Sylvan and I have known each other since we were 16 years old, and the only reason probably why we knew anything about Pony was he sent me like a LinkedIn a year before that was like, well, the only time second time LinkedIn's ever been valuable, was when he sent me a thing and said, ooh, look what I built. The one other time that LinkedIn was valuable was when Pat Helland sent me a message and was like, hey, so I was sitting at my desk and a bunch of my colleagues came over and said, you got to see this, and showed him the program for VelocityConf. And he's like, that looks really cool. Thank you.
Okay.
Thanks.
So since there's sports around, I think we're allowed to stay here for a little bit. So if you want to ask more questions of Sean T. Allen, not the person that is like problematic, it's also the person that we like, we can stay around.
Question, who here has never been to a Papers We Love up until tonight?
Wait, San Francisco?
Yeah.
Yeah.
San Francisco. Oh.
Good.
Oh, okay. That's awesome. Please continue to bring your friends and also like junior programmers, interns, like people who don't get out as much. Please bring new people into this.
Also, last true story about Sean, he has the ADA compilation rules tattooed in one of his arms. You're going to have to ask him about which one it is.
Wait, what do I have?
The ADA compilation rules.
Oh, that's true.
$1 million compiler. Woo! Okay. Thank you, everybody, for coming, and we'll see you next month.
Thank you, Patrick and GitHub.